Hello and welcome to this session. In this session, I'm going to talk about the moment and the moment generating function in relation to the distribution functions. Moments are numerical measures of the shape and characteristic of a probability distribution. They're usually calculated by taking the expected value of a function of a random variable, usually raised to some power. The resulting number is a measure of the distribution central tendency. And central tendency here we mean where the data tends to cluster, the dispersion, how the data is spread out, the skewness, which looks at the symmetry or the asymmetry of the distribution, and the kurtosis, which is the degree of pickedness or the flatness of the distribution. Now, the other moment of a random variable x about the mean, also known as the Rth central moment, is usually denoted by mu r, and we define this as the expected value of x minus mu raised to power r, where r is an integer taking the values from 0, 1, 2, and so on. So it's a non-negative integer. So mu here is the mean of the random variable. Remember, in previous lecture, we said the mean, which sometimes we denote by x bar, the mean of a distribution is expressed as the integral from minus infinity to infinity x times f of x, where f of x here is the probability density function. So the mean mu is the mean of the random variable x. And mu r is what we are calling the Rth central moment, or the Rth moment of the random variable about the mean. So when r is 0, we write mu naught, which is the expected value of x minus the mean raised to the power of 0. And remember, when any number raised to power 0 is 1, so this is the expected value of 1. Now, the expected value basically when we talk about the expected value, we talk about the mean of that value, of that random variable. The mean of 1 is just 1. So that the mean of 1 is just 1. If we put r is equals to 1, then we forget the first moment, mu1, which is equals to the expected value of x minus the mean raised to power 1. Now, when we work out the mean of x minus the mean, we are going to get 0. Whenever we have a set of data, whenever you take any set of data, say you have a simple data like 1, if you have a simple case like x taking the values like 1, 3, say 3, we have 5, and say maybe 4, so that x bar, or the mean, x bar, which we can denote by mu, is equals to 1 plus 3 plus 4 plus 5 divided by 4. This will be 1 plus 3 plus 4 is that 1 plus 3 plus 4 plus 5 is 13. So we get 13 over 4, which is 3.25. So if we now subtract 3.25 from each of the values there, then add the result. That is 1 minus 3.5 plus 3 minus 3.5 plus 5 minus 3.5 and plus 4 minus 3.5. If we work out all this, the result is the same as writing. You say we can expand this and write this is the same as 1 plus 3 plus 4, or rather plus 5 plus 5 plus 4 minus 3.5 plus 3.5 plus 3.5 plus 3.5. This is 4 times because we have 3.5 here, 3.5, 3.5, and 3.5. Now, notice that the first bracket here will get that in, and also the next one, the other bracket, the second bracket, we have 3.5 times 4, which is also 13, so that the result is 0. 0 divided by, we are getting the expected value, 0 divided by 4 is 0. So whenever we write x minus x bar or x minus mu in this case, and we try to find the expected value of this, we'll get the result as 0. So mu1 is 0, and when we write mu2, this will be the expected value of x minus mu squared, which is basically the variance of the distribution. So the second moment about the mean is equals to the variance of the distribution. So basically, when we talk about mu r, the rth moment, the expected value of x minus mu raised to the power of r, which by definition of the expected value is given by the integral from negative infinity to infinity, x minus mu raised to power r multiplied by f of x, then we integrate with respect to x. And clearly we can say from here is that when we use this definition, we can clearly see that when we write mu r is equals to the integral from minus infinity to infinity, x minus mu, which is the mean of the distribution, raised to power r times f of x dx. We see that when we write mu 0, the result will be the integral from negative infinity to infinity, x minus mu raised to power 0 times f of x, and we integrate with respect to x, and this will be the integral from minus infinity to positive infinity of f of x dx, because the any number raised to power 0 is 1. So this quantity here, which we are raising to power 0, will give us a value of 1. Now, this integral here gives the total area under the function f of x. Since f of x is a probability density function, the total area under the curve must be equals to 1, so that this is equals to 1. If we write mu 1, which is the integral from minus infinity to infinity, x minus mu raised to power 1 times f of x dx, then we see that we can break this into 2 and write the integral from minus infinity to infinity, x times f of x dx minus the integral from minus infinity to infinity, mu times f of x dx. Now, since mu is the mean, is a constant, the mean of a distribution is a constant, so we can push it forward here. And then the first integral The first integral basically gives the mean. This one is, by definition, the mean of the distribution. So we can write mu, which is the mean of the distribution, minus mu, the integral from minus infinity to infinity, f of x dx. Now, f of x being a PDF, then this integral will give us a value of 1, because it gives the total area under the curve. So we get mu minus mu times 1. And mu times 1 is mu, so we get mu minus mu, which is equals to 0. So we see that the first moment about the mean is equals to 0, as we had said earlier. So we look at the moments about the origin. So if we replace now the mean mu with 0, that is, we find the moment about 0. So we had the expression that mu r is equals to the expected value of x minus mu, where mu is the mean raised to the power of r. So suppose now we want to find the mean about the origin. So we replace mu here with 0. Then we get the moment, the other moment becoming the expected value of x raised to the power of r. Now we call this the other moment about the origin, and we use the notation mu prime r. Mu prime r. R again takes the values from 0 to 1 to 2 and so on. So that if we find the case where r is 0, the expected value of x raised to power 0, which is x raised to power 1, will get 1. The first moment about the origin, the expected value of x raised to power 1, and you see now when we write mu prime 1, this is the expected value of x raised to power 1. This is now the integral from minus infinity to infinity of x times f of x. And by definition, this is the mean of the random variable, which we are denoting by mu. If we find mu prime 2, the second moment about the origin, x raised to the power of 2, we get the integral from minus infinity to infinity, x squared f of x dx. So we can easily work out this integral. We can easily work out this integral, which will give us the mean, the other moment about, or rather the second moment about the origin. So in general, the other moment about the origin is given as the integral from minus infinity to infinity, x raised to the power of r times f of x. Then we integrate with respect to x. So we now look at the moment generating functions, what we shall denote by MGF. So a moment generating function is a mathematical tool that is used to describe the properties of a probability distribution. It is a function, as the name suggests, that generates the moments of a probability distribution. So the MGF of a random variable is defined as the expected value of an exponential function of that variable. So the importance of MGF in statistical analysis lies in the ability to uniquely characterize probability distributions. In other words, if two random variables have the same moment generating function, then they have the same probability distribution. And this property allows us to use the moment generating functions to derive important results in probability theory and statistics. One of them is the central limit theorem, though we will not be going into that extent in this course. So the moment generating function of a random variable x shall be denoted by m subscript x, which is a function of t. We shall define this as the expected value of e raised to power tx, e here being the base to the natural logarithm. So we write the expected value is, remember, the expected value, whenever we write the expected value of some function g of x, we get the integral from negative infinity to infinity, g of x times f of x, where f is the probability density function. So in this case, when we write m x, a function of t, the moment generating function, which is the expected value of e raised to power tx, this would be the integral from minus infinity to positive infinity of e raised to power tx multiplying f of x. And then we integrate with respect to x. When we integrate, the resulting function is a function of t. The resulting function is a function of t. So we shall apply the McLarens theorem or McLarens series. Remember the McLarens series, which says that the McLarens theorem states that if we have some function f of x which is continuous and differentiable at x is equals to 0, that is, if some function f of x is differentiable at x is equals to 0, then f of x can be expressed as an infinite series, which is of the form f of 0 plus x f prime of 0 plus x squared over 2 factorial f double prime of 0 plus x raised to the power of 3 all over 3 factorial times the third derivative evaluated at 0, and so on. So that any term can be expressed as x raised to power n all over factorial n multiplied by the nth derivative evaluated at x is equals to 0. This is an infinite series. Now, if we consider the case where the function f of x is equals to e raised to power, say, ax, then we may need to find, we will need to find f of 0, which is e raised to power 0, and e raised to power 0 is 1. Then we need to find the first derivative. You see we need to find the first derivative, the second derivative, the third derivative, and so on. So we differentiate this function to get f prime, which is e raised to power ax. Then we find the value of that at 0, which is a times e raised to power 0, and this is equals to a. We find the second derivative, which will be a squared e raised to power ax, and we find its value when x is equals to 0, which will give us a squared times e raised to power 0. We find the third derivative at any point x. This will be a raised to the power of 3 e raised to power ax, and its value when x is 0 will be a raised to the power of 3. And we say that if we continue like this, we can write the nth derivative at any point x will be a raised to power n times e raised to power ax, and its value when x is 0 will be a raised to power n. Now, if we substitute these values into our series here, the first term is 1. Here we write ax. This will be a squared times x squared over factorial 2. This will be, this one is a cubed, which will multiply this. So our series for the exponential function e raised to power ax becomes 1, then plus ax, then plus a squared x squared all over 2 factorial. Then the next term is a cubed x cubed all over factorial 3, and so on, so that any term will take the form a raised to power n, x raised to power n, all over factorial n. So now we want to consider now our function, the function that we had earlier there. So if we go back to our function now, we wanted to find the moment generating function, and we had a series e raised to power tx. We were looking for the expected value of e raised to power tx. So if you look at what we have here, if we want to find e raised to power tx, we can replace a by t in this series. So we're going to have the first term will be 1, the next term will be tx, the next one will be t squared x squared all over factorial 2. The next one will be t raised to the power of 3, x raised to the power of 3 all over factorial 3, and so on, so that any term will be t raised to power n. Any term will take this form all over n factorial. So this will be our series for e raised to power tx. And now if we want to find the moment generating function, which is the expected value of e raised to power tx, the expected value of e raised to power tx, then this is the same as writing the expected value of 1 plus tx plus t squared x squared all over factorial 2 plus t cubed x cubed all over factorial 3, and so on. It is the expected value of that. So that in this case we can write the expected value of 1. We saw that the expected value of 1 is 1 plus the expected value of tx plus the expected value of t squared x squared all over factorial 2, and so on. So our series will be of this form. Our series will now be of that form. So the expected value of t, this is what we have here, and you can say now we write, because x is our random variable, then we can write this one. The first term is obviously 1. The expected value of 1 is 1. Then we can write plus t times the expected value of x plus t squared all over factorial 2 times the expected value of x squared. The next term would be t cubed all over factorial 3 times the expected value of x raised to the power of 3, and so on. So that any term we can write it as t raised to power n all over factorial n times the expected value of x raised to the power of n. If we go back to what we had, where we had defined our moments, earlier. If you look at how we have defined our moment about the origin, the 0th moment about the origin is 1. The first moment about the origin is equals to the expected value of x. The second moment about the origin is the expected value of x squared, and so on. So that if we write the nth moment about, that is the nth moment about the origin, it will be the expected value of x raised to power n. So now, looking at what we have here, you can see that the first term is obviously the 0th moment about the origin. In the second term, we have t times the first moment about the origin. Then t squared for factorial 2 times the second moment about the origin, and so on. So this is how we can write our series, which is the moment generating function. So the first term, which is 1, is equals to the 0th moment about the origin. The second one is the first moment about the origin, which is equals to the mean of the distribution. Then we have the second moment about the origin times t squared over factorial 2, and so on. So that we see we have an infinite series in the series into the powers of t. The coefficients of this are the moment, the coefficients of this moment generating function gives the moments about the origin. These coefficients, they are the moments about the origin. Let's do an example. We are given a function here. You're told that a continuous random variable has a probability density function f of x, and this probability density function is defined as 2 times e raised to power negative 2x whenever x is greater than or equals to 0, and is equals to 0 whenever x is less than 0. The problem here is to find the moment generating function and then find the first 4 moments about the origin. So we shall find the moment generating function, which is the expected value of e raised to power tx. And by definition, this will be the integral from minus infinity to infinity of e raised to power tx times f of x, and we integrate with respect to x. But now, when we are dealing with a function here, you see that the function is 0 whenever x is negative, and the function is 2 times e raised to power 2x whenever x is non-negative. So that in this case, we have the 0 here is the boundary. On this side, f of x is equals to 0. On this side, f of x is equals to 2 e raised to power negative 2x. Now, since the integral of 0 is 0, the definite integral of 0 is 0, when we start from minus infinity on this side and come all the way to 0, we'll be working out the integral, the definite integral of 0, which will be 0. But from 0 to positive infinity, now we have a non-zero function. So we shall write the integral from 0 to infinity, e raised to power tx times e raised to power negative 2x dx. There is a coefficient 2. I'll write it here, 2 times that. So that we write 2 integral from 0 to infinity, e raised to power negative 2 minus t x dx. And integration of this will give us, remember we are integrating with respect to x, so we are going to treat t as a constant during this integration process. So we get minus 2 over 2 minus t e raised to power negative 2 minus t times x, and x increases from 0 to infinity. So that we get minus 2 divided by 2 minus t. So when x goes to infinity, this becomes a very small number, so this approaches 0. And when x is equals to 0, if we put x as 0 here, we get e raised to power 0, which is 1. And so we get this is 2 divided by 2 minus t. We can factor out 2 in the denominator so that we get this is equals to 2 divided by 2 into 1 minus t over 2. And this reduces to 1 over 1 minus t over 2. This is the moment generating function. This is the moment generating function. And we need to expand this. We're now going to expand this using the binomial theorem. Binomial theorem. The binomial theorem is useful for the expansion of the form 1 plus x raised to the power of n, and is usually given by 1 plus nx plus n times n minus 1 divided by factorial 2 times x raised to the power of 2 then plus n multiplying n minus 1 multiplying n minus 2 divided by factorial 3 multiplying x raised to the power of 3. This is the binomial series. In our case, we have 1 divided by 1 minus t over 2, which we can write as 1 minus t over 2 raised to power negative 1. So we are going to consider the case where n is equals to negative 1 and x is equals to minus t over 2 in our series here. So we are going to substitute n, the power n here is minus 1. And in place of x here we have minus t over 2. So we can replace n with minus 1 and x in this series, in the binomial series, with negative t over 2. So we write 1 minus t over 2 raised to power negative 1 is equals to 1 minus is it minus what? Minus t over 2, then minus n, which is 1, minus 1 minus 1, which is n minus 1. We divide this by factorial 2. Then we multiply by minus t over 2 raised to the power of 2. The next term becomes minus 1, minus 1 minus 1, then minus 1 minus 2 divided by factorial 3. Then we have minus t over 2 raised to the power of 3, and so on. Those are the successive terms of that series. So that we get a 1 minus, this will now be plus a half t. Then minus 1 is minus 2. So minus 2 times minus 1 becomes positive 2. 2 divided by 2 factorial is 1. So this becomes plus 1 over 4 t squared And similarly, the next term becomes 1 over 8 t raised to the power of 3, and so on. So in this case, I can get the next one will be, if we work out the same way, will be 1 over 16 t raised to the power of 4. And 1 over that 2 t raised to the power 5, and so on. This is the moment generating function. This is our moment generating function, which we are going to compare with the general one. We had seen that the moment generating function can be expressed as 1 plus mu t plus mu 2 prime t squared all over factorial 2 plus mu prime 3 t raised to power 3 all over factorial 3, and so on. So if we equate the coefficients here, we can see that if we equate the coefficients, we equate this, the coefficients of the corresponding powers of t. We see that the mean is equals to a half. Then the next one, we equate this with this. See that here we have 2 factorial, so we shall write mu prime 2 all for factorial 2 is equals to 1 over 4, which implies that the second moment about the origin will be equals to 2 factorial divided by 4, which is 1 over 2. Then we equate this to this. See that there is a 3 factorial here. So we shall write mu prime 3 all over 3 factorial is equals to 1 over 8. And this implies that that moment about the origin will be equals to 3 factorial over 8. 3 factorial is equals to 6. So we get 6 over 8, which is 3 divided by 4, or 0.75. We can equate the next term. This one, all over 4 factorial, is 1 over 16. So we can write the fourth moment, all over 4 factorial, is equals to 1 over 16. And this implies that the fourth moment about the origin will be equals to 4 factorial all over 16. 4 factorial is 24. So 24 over 16 is the same as 3 divided by 2. So those are the moment about the origin from the moment generating function. So we first find the moment generating function, which is this. We expand that using the binomial series expansion. And now we compare with the series that we had obtained earlier. And we get the first moment, the mean, the second moment, which is obtained by equating the coefficients of t, the third moment, the fourth, and so on. We have a second example, which can be done the same way, but here we need first to find the value of k. To find the value of k, you just need to integrate this function from negative infinity to infinity, e raised to power negative kx, and equate the result to 1. Because this being a probability density function, then the total area under the curve would be 1. So when we integrate, we get the value of k, which is 5, and then we substitute. And then we can find the moment generating function. We can find the moment generating function the same way as we have done in the previous example. So we find the moment generating function, which is the expected value of e raised to power tx. So again, we integrate, we see that the function here is 0 for x being negative. So we only consider from 0 to infinity, where the function is non-zero. So we simplify and then integrate. We expand this using the binomial series, and we get the moment generating function. Once we get the moment generating function, we consider with the general one, which we write as 1 plus mu t plus mu prime 2 t squared all for factorial 2 plus mu prime 3 all for factorial 3 times t raised to the power of 3, and so on. So we equate these coefficients. Like if we want to find the third moment, we equate this coefficient to 1 over 125, and then make mu 3 the subject. So in this case, we can find the first moment, which is the mean, the second moment, the third, the fourth, and so on. Now we have a third example. I have a continuous random variable x as a probability density function f of x, which is defined by this expression here for x between 0 and 3, and it is 0 elsewhere. The problem is to find the first 4 moments about the origin. So here again, here we may not, it may not be easy to find the moment generating function. We can work out the moments directly rather than finding the moment generating function. The moments about the origin. See that the moment about the origin, mu r, is given by the expected value of x raised to the power of r, which is the integral from negative infinity to infinity, x raised to the power of r, f of x dx. So when we find the first moment, will be the case where r is 1, and we get the integral from minus infinity to infinity, x raised to power 1 times f of x dx. But our function here ranges from 0 to 3. That's only the region where the non-zero values occurs. So in this case, we shall integrate from 0 to 3. Then we have x times 4 alpha 81x into 9 minus x squared. And we integrate with respect to x. So this will be the mean of that distribution. So this will be the mean we work out. And first we can write 4 alpha 81. Sorry, we have the integral from 0 to 3. So we multiply out here x times 9, that is 9x squared. Then x times minus x squared will give us minus x raised to the power of 4 dx. So this is the function to integrate. So we simplify first. We don't integrate when it is like this. We simplify first, then integrate. Once we do that, then we get the mean is 1.6 as we have here. If we want to find the second moment about the origin, then now this will be the expected value of x squared. So we shall write the integral from 0 to 3, x squared times 4 alpha 81x into 9 minus x squared. And you see, we integrate with respect to x. You notice that this integral is just similar to this, only that now we are multiplying by x squared and not x. So we shall just get 4 alpha 81, then integral from 0 to 3, 9x cubed minus x raised to power 5. And then integrate with respect to x. That will give us the second moment about the origin. For r is equals to 3, we work out the same way, and we get the value. And for r is 4, the fourth moment, we work out, the method is exactly the same. Now, when we want to find the moment about the origin, about the mean, first, we have seen that the mean is 1.6. We have obtained that, the mean, we have obtained the mean up here as 1.6, so, which is the first moment about the origin. That's the mean of the distribution. So if we want to find the other moment about the mean, then we shall write mu r is equals to the expected value of x minus 1.6 raised to the power of r. 1.6 is our mean. And now we can consider the case when r is 1. When r is 1, we get mu1 is equals to the expected value of x minus 1.6 raised to the power of 1, which is the integral from 0 to 3, x minus 1.6 multiplying 4 over 81 into 9 minus x squared, which is our function. And we integrate with respect to x. That's what how we should work it out. But definitely, as we had seen earlier, the first moment about the mean is always equals to 0. So we don't need to work out that. But when now r is 2, when r is 2, we need to work out. We write in general mu r is equals to the integral from minus infinity to infinity x minus mu raised to the power of r f of x dx. So when r is 2 and the integral and the non-zero values rise between 0 and 3, the non-zero values of the function, then we shall write mu2 is equals to the integral from 0 to 3 x minus 1.6, which is our mean, raised to the power of 2 times f of x, which is 4 over 81, multiplying x into 9 minus x squared. And we integrate with respect to x. Now, sometimes it is maybe easier to expand this by noting that x minus mu squared can be expanded as x squared minus 2x mu minus, plus mu squared. And then we find the expected value of x squared, the expected value of x, and then we add mu squared. The expected value of x is mu, so that this will be minus 2 mu times mu, which is minus 2 mu squared. Notice that when we write x minus mu squared, as we had seen earlier, is the same as x squared minus 2 mu x minus, or rather plus mu squared, so that when we write the expected value of x minus mu squared, this will be the expected value of x squared minus 2 mu times the expected value of x plus the expected value of mu squared. The expected value of the mean, the square of the mean is just the square of the mean. But this one is the mean, so that this becomes the expected value of x squared minus the square of the mean. Now, because we know the square of the mean is 1.6, and we have also obtained the expected value of x squared in the first part here. The expected value of x squared is the second moment about the origin, which is 3. So that one we have already obtained. So it means that we can then substitute here as 3 minus 1.6 squared, which will give us the value, that we have here, 0.44. When r is equals to 3, we can work out the same way. We can expand this. One way is to integrate directly, but integration directly may take more time than expanding. Of course, we can expand this using the binomial theorem. When we write x minus mu raised to the power of 3, this will be x raised to the power of 3 minus 3 mu x squared minus 3. This will be plus 3 mu squared x minus mu raised to the power of 3. So when we want to find the expected value of x minus mu raised to the power of 3, then we get the expected value of x raised to the power of 3 minus 3 mu times the expected value of x squared minus 3, this is plus 3 mu squared times the expected value of x, then minus mu raised to the power of 3. Now the expected value of x cubed we had obtained in the first part. The expected value of x cubed, which is the third moment about the origin, we had obtained a value of 6.1714, which means that we can substitute here as 6.1714. Then we can write minus 3. Mu is 1.6. The expected value of x squared is 3. That was the second moment about the origin. Then we have plus 3. Mu is 1.6. So we square that. The expected value of x is 1.6, which is the mean. And then we have 1.6 raised to the power of 3. So by expanding that, we see that we can express the moment about the mean in terms of the moment about the origin. And then we can use the results from the moments about the origin and substitute to get the moment about the mean. So when we do that, we get this is the third moment about the mean, and also the fourth moment about the mean. So we can always expand this by the binomial theorem. And once we expand, we see that the moment about the mean can be expressed in terms of the moment about the origin. So I think for now I'm going to stop at that. In the next session, we shall talk about the joint distributions, the joint probability distributions.